today's our topic is balanced binary search tree presented by Anmol, Animesh and Dipen Shukla, guided by Professor Dr. Prasanjit Gupta. So what is balanced and unbalanced binary search? A balanced binary search tree is a tree with the height of its trees at each level is equal, or there is a difference between one in their height at each level. So if we see that the middlemost tree which root has 1 2, it is not a balanced binary search tree because it's the height of its subtrees rooted at right side which has more height than the subtree is rooted at the left side, because there is a no left subtree. That's why. So if we see that the rightmost example, it is a perfect example of balanced binary search tree because there is a subtree rooted at 2 or 6 has equal size. Rooted at 2 has equal size. Equal size means the equal height at each level. And if we see that the root 4, here's 2 and 5, so it is also a balanced binary search tree because the height at each level is equal, or either there is the height difference between the height is 1. So here is 0 1, or here is 0. 1 minus 0 is 1. So here is the difference of height is 1. So that's why it is a balanced binary search tree. So you might have a question, why balance? Let's see example of A field. It is a type of balanced binary search tree. We have already a binary search tree. It is also helpful in insertion, deletion and searching process. So if we see the average case of insertion, deletion and searching in binary search tree is order of log n time. But in worst case, it reaches to big O of n. That's why we need a search structure in which we can work very efficiently in order of log n time. So that's why we use balanced binary search tree, which work in order of log n time. So what is height and a balance factor? A height, as we usually calculate from the root, from the leaf nodes. So here 0, 1 and so on. And what is the balance factor? Balance factor is the height of left subtree minus right subtree. Okay. So if here you can see the 0, 1, 2 height at, if we want to calculate the balance factor there, it will be the height of a right subtree minus the left subtree, or vice versa. So left subtree height is 1 minus 1 minus minus of 1, because there is no subtree. We calculated, we put minus 1 right here. So that's why 1 minus minus of 1 is 2. So it is a balanced? No, it is not a balanced binary search tree. The reason is behind that a balanced binary search tree has 1, 0 or minus 1 balance factor, either any three of them. Okay. Let's see the insertion part in the left child of left subtree. Left child of left subtree, if we insert the x, there is distortion in the tree structure. To maintain this distortion, we rotate this tree structure. So in the left, when we insert from the left child of the left subtree, we rotate at the right hand side. So after rotation, the u part will become at the right side of the v, and v become the root node. So here it become the root node, right side, and y and z. So similarly, with the help of example, let's say it. Let's suppose we inserted 0.8. Due to this, there is a distortion in the structure. So after rotation, the root will be 3, 5, 8 here, and the 8 will be rightmost part of the rectangle. So, and suppose the imbalance is due to the insertion in left subtree of the right child. So there in the case, double rotation case arises. First, the rotation in the left hand side, then rotation in the right hand side. Before rotation, you can see here, and after rotation, what will happen? The W will be the root node. Because of the left rotation, it will be the here, and due to the right rotation, the U will be this part. U will be left, and sorry, V will be left and U will be right part. So after rotation, we will have this scenario, Thank you. And further, I give the mic to animations.
As well, my friend introduces ABL tree and the insertion process and rotations, single and double rotations around this ABL tree to balance this ABL tree. We will see the example of double rotation. So basically here this is the balanced ABL tree. A balance factor is 1. Now if the balance factor will change to 2 or minus 2 at every level, we have to make a rotation. So let's see example. Like here we have inserted the 3. So basically it is based on binary substitute, so it will be at left of the 4. So after inserting, now we will check the balance factor. So add 3, balance factor is 2 minus 0. So it is at 3, it is 2. So we have to make a rotation. So for that we will first make rotation, right rotation for this line. So it will come down to the 5 or 4, 5 and 8. In the next step we will follow. So 5 and 8 will be there. So 5 and 8, for that the balance factor at 4 will change. So balance factor at 4 will now become 2. So like here 5, here it is 8. So we have to make this rotation. And when we make this rotation, 3 and 1 will be at left of this. So where it will go? It will go to the right of the 3, because we have to follow the binary search structure. So the structure will become like this after rotation 4 and 3. And this 3.5 will be at the right of the 3. So we will see a standard example to understand completely how the insertion work in the balanced binary search tree or ABL tree. First we will insert C and then 2. So after inserting 1, the balance factor at the level will become 1, and here it is minus 1. So 1 minus 1, it is 2 at the level. We will make a right rotation at 2. So it will become balanced. Now let's add 4. So it is no changes in balance factor, means it is not 2 or minus 2 at any level. Now when after inserting 5 at the level where this node 3, we will see that here it is 0, here it is 2. So 0 minus 2, it is minus 2 at level 3. So we have to make a rotation. So we will make rotation and at level 3, and after rotating the structure will become balanced. Now let's add 6. So when we add 6 at the level of 4, the balance factor will change and we will make rotation and shift 4 to the like 2 and 1 to the left of the 4, and the structure will become like this. And after that we will add 7. So the balance factor at 5 will change and we have to make a rotation. So we will make a single rotation at 5 and it will shift to the left of the 6. Similarly we will add 16, and due to that we have to maintain, there is no requirement to maintain the balance factor because it is not 2 and minus 2 at any level. After adding 15, now the balance factor at 7 will change and we have to make a rotation. So 15 will become after rotation at 7 will become left of the 15 and 16 will become right after 15. Now we will add 14, and similarly we will follow further, and the balance factor at the 7 will change, and after making 2 rotations, double rotation, confirming the A balance structure. So similarly we will balance by making the balance factor at every level at max 1 or minus 1. So my friend Dipen will explain you deletion with the similar example.
Now come on the deletion part of the balanced binary search tree. In this ABL tree, we are going to see the really simple case that if we have to delete this node 17 which is present at the leaf node, then we just have to delete it in the same manner as we do in binary search tree. What we have to do, just remove it from the tree. But what is the difference between AVL deletion in AVL tree and binary search tree? That is, we will again check the balance factor of the tree. If it is not maintained, then we will again change the um, the shape of this tree. So but this is not required in this case. We will remove this leaf node without changing in anything. Now again come on the second case. If we want to remove this 12 from this tree, then we have to just remove this node, and then we will do the right shift. This green part will go on the red part. This is a left shift in the AVL tree, which will again maintain the balance factor, because balance factor get disturbed after removing the 12. Now if we see the here, that is the same thing. If we remove 12, then what we have to do is just to shift left shift. 20 will go upside, and the 2 will come at the left of the left of 20th node, and 30 will remain same as the right node of 20. Now to do that, we have to remove. This is the showcase of it, that how we did it. Okay, 20 will go upside, means first node, 20th go upside, and here in the second 17 is written, which comes on the left side of 20, and 30 came on the right side of the 30. This is how we maintain the balance factor of this AVL tree.